Let's move along here and take a look at our Module 6 lecture on Portland cement concrete. This lecture, the topics that we'll cover are concrete pavement, white topping, inspection and quality control, special concretes, and test procedures. Let's take a look at concrete pavements. Rigid or concrete pavements are used on about 5% of hard surface roads in North America. And if you look back in the 30s and the 40s, concrete was the main road surface that they used before asphalt pavement came into play. Their usage is increasing due to the growth in highway or traffic loads and the large number of freeways or other high capacity highways being built in North America. And we see this different times. You'll see some concrete pavement machines on the roadways. Depending on who specs it out and what type of surface that's being used, we either have asphalt or concrete. A major problem with concrete pavement is the volume changes that take place. A concrete slab shrinks as it cures or hydrates. Also, there's continual shrinking and expanding during the life of the pavement due to temperature changes and things like this. And we also have to remember that concrete, even after it hardens, it's going to absorb water and moisture. To allow for these volume changes, most concrete pavements have joints or at least develop cracks. And what happens, and when you see bridges and things like this that are poured with concrete, you're going to see expansion joints. And that allows that bridge to expand. In the winter months, concrete's going to shrink. It's going to contract on us. In the summer months, it's going to expand. So that allows that bridge section to move whatever the tolerance level is. There are four main types of these pavements. We get plain pavements. They have soiled or formed joints. Cracks form beneath the joints within a few days after the concrete is poured. As shown in the figure, of course, it's in the PowerPoint presentation that's part of this module. And the load is transferred between the slabs as the interlock between the crack faces of the concrete below the surface or the surface joint. Joints are usually 13 to 20 feet apart, although some specifications allow a maximum of 15 feet. We have doweled pavements. These are constructed with smooth steel dowel bars under the soil joints to transfer the load between the slabs more efficiently. Spacing of the joints is similar to that for plain pavements. We also have reinforced pavements. These are lightly reinforced slabs with load transfer at the joints provided by heavy reinforcing steel bars. Joints can be 40 to 100 feet apart, although some specifications allow a maximum of 42 feet. One or more transverse cracks may form between the joints. However, they are held together by the reinforcing steel and the load is transferred effectively. Continuously reinforced pavements. These are constructed with relatively heavy reinforcement. No construction joints are built. Many thin transfer cracks are formed at close intervals on the pavement. They are held tightly together by the reinforcement and load is transferred effectively. Concrete joints are usually cut in the pavement with the concrete saw to a depth equal to a quarter or 1/4 of the depth of the slab as soon as the concrete has stiffened sufficiently. Careful control of the timing of the cut is required. Concrete must be hard enough so that the surface does not tear during the cutting. However, waiting too long or a long time, a day or two, may result in the formation of random cracks. Joints must be sealed to keep the water out, dust, and other debris to ensure that the pavement or the movement of the slab can continue to occur. Construction joints are also required between pours constructed at different times and between lanes that we have. Also, dowels or keys are placed in these joints to act as a load transfer device for the construction purpose. Special requirements for subbases and subgrades for concrete pavements were discussed, of course, in other presentations that we had. Thickness design procedures are outlined in the AASHTO Guide for Design of Pavement Structures, and of course the CPCA Booklet Thickness Design for Concrete Highway and Street Pavements. Research conducted under the SHRP described various improvements to the concrete technology used in highway construction and maintenance. Included were types of repair projects where the highways could be opened to traffic in 2 to 4 hours. And of course, this is a tremendous improvement for minor repairs to busy highways. And as we all know, we all sit in traffic at times and it becomes a nuisance or a nightmare. Slip form construction is now used for most concrete pavements. The base is prepared and the grade and aligned requirements laid out for the paving train. No slump concrete, sump less than an inch, is placed on the roadbed in front of the train. The concrete is disturbed, vibrated, screed, and finished by the paving train as it proceeds. As the concrete is stiff enough to retain its shape after it has been placed, no side forms are required. The slip form method is also used for towers and silos. Example, the CN Tower in Toronto was erected to a height of 1,500 feet in a little more than 100 days using the slip form method. Tight quality control and consistent concrete are necessary for the successful slip forming. Modern concrete paving train operations with a slip form paver are shown in the PowerPoint presentation for this module. Pavers automatically control alignment and profile. The paver is usually followed by a burlap drag to texture the surface and a tinning machine to make transverse grooves, both to provide skid resistance. The tinning apparatus makes small grooves with a spring steel tins. Of course, the application of the curing process can be looked at within the PowerPoint presentation. White topping refers to the growing practice of using concrete overlays over failing asphalt surfaces. Asphalt pavement failed due to rutting, raveling, fatigue, temperature cracking, and other causes. Washboarding or bulging due to horizontal forces of intersections, hydroplaning due to water and ruts, spring load restrictions due to weakened bases are also problems that we face within our paving processes, or environmental concerns that attack our paving surfaces. For resurfacing with asphalt, a considerable amount of preparation is usually required. The old pavement must be leveled, and perhaps the base course will have to be replaced. Often, the resurfacing layer does not last long as cracks are reflected and problems with the base remain. Maintenance costs may be substantial. For these reasons, concrete overlays may be considered. Little or no remediation of the asphalt surface is required unless asphalt ruts are over 2 inches in depth. Concrete spreads the traffic load over a large area, protecting the base. Maintenance costs for the concrete pavements are much lower, and the surface may last 20 to 40 years. Also, the increasing cost of asphalt is making concrete more attractive, even though the initial costs for the concrete pavement are substantially higher. Our slab thickness design. The slab thickness design depends on the following. We want to look at the supporting strength or characteristics of the existing asphalt pavement, the flexural strength of the concrete overlay, the amount of traffic or truck traffic expected over the design period, and also we have a K value for the asphalt surface, can be obtained from the graph using the K values for the subgrade that we have, of course based on the CVR or the R strength values and the thickness of the base and the asphalt. The flexural strength of the concrete can be estimated from the compressive strength by using the flexural strength formula. Tables by the American Concrete Pavement Association give the pavement thicknesses that are recommended for various types of truck traffic that we're going to have. Recommended minimum slab thickness requirements for various types of roads are shown in the tables provided within the PowerPoint presentation and are labeled recommended minimum slab thickness for white topping. The thickness of the slabs usually varies from about 4 to 12 inches. Recommended joint spacing varies from 7 feet to 4-inch slabs to 21 feet for 12-inch slabs. Ultra-thin white topping. Ultra-thin white topping refers to the construction of the surface course only 2 to 4 inches in thickness. Usually a high-strength fiber reinforced concrete is used. The bond between this type of topping and the asphalt is quite strong, and the joint spacings are much shorter than normal. This usually is used in situations where substantial thickness of the asphalt exists or where multiple layers of asphalt overlays have been placed over time. Many projects have been open to traffic quite quickly, and details regarding the design and construction of white topping surfaces can be found in the Engineering Bulletin, White Topping, State of the Practice, of course, published by the American Concrete Pavement Association. If we look at the inspection and the quality control, the quality of concrete and the construction operations must be monitored to ensure that final properties are as specified. The engineer inspectors are responsible for their phase of this portion of the project. New types of equipment and test methods will allow more dependable and accurate quality control operations in the future. The plant inspector is responsible for ensuring that the materials and the mixing procedures comply with the design specifications of the mix. The inspector must monitor the quality, stockpiling, and handling of the materials and accuracy of the measurement devices and mixing operation, and the quality of the batches being loaded. If we continue to look at inspection and quality control, sampling and testing of the aggregate and concrete as specified by the owner, agency, design professionals are also required, and it's very important. Gradation of the aggregates must be checked periodically and whenever there is an apparent change in the texture, the size, and so forth. Uniformity of the sand is especially important. The fineness modulus should not vary more than 0.20 from the design values. The moisture content of the aggregates should be measured at the beginning of each day and whenever there's a change or a change is apparent. The mix design is based on the aggregates in the saturated surface dry condition, and the batch design must be adjusted quickly if moisture content changes. The speedy moisture tester is often used to find the water content of the sand. A known mass of the sand is measured on a small balance and is placed in a pressure cell. A reagent is added to the other part of the cell. When the two parts are joined and the cell shaken, the water and the reagent produce a gas. The pressure resulting from the gas varies with the amount of gas produced, and therefore the water content of the sand is calculated or determined. The site inspector. The site inspector must monitor the quality and consistency of the concrete as it arrives and the placing, consolidating, finish, and curing operations. This is very important because the design professional has laid out the specifications. The site inspector looks at those specifications and makes sure that they are met. The slump test is the main method used to determine the quality and the consistency of the plastic concrete at the site. Air content tests are also required for air entrained concrete. 2 slump tests are usually made on the first load each day on samples taken when the load is approximately 15 to 85% discharged. This measures the consistency of the mixing, and the 2 test results must fall within a narrow range, plus or minus a ½ inch for low design or low slump designs, and a plus or minus 1 inch for medium slump mixes or designs. Air tests are taken as often as required until consistent results are obtained, and of course periodically thereafter. Temperature records must also be maintained. Very important again, what is that temperature during the day? The maximum and minimum allowable concrete temperatures have been discussed, of course, earlier on. Let's take a look at the compressive strength that we're dealing with concrete. The compressive strength test requires the casting, curing, testing of 2 standard cylinders. The test result is obtained by averaging the 2 strengths that we have. Air content and slump tests are taken as the cylinders are made. After casting, the cylinders must not be disturbed and must be protected from temperature changes or drying environments. After 24 hours, the cylinders can be transferred to the laboratory, removed from the mold, and stored at the required temperature and humidity. Compressive strengths are acceptable if the average of any 3 consecutive strength tests is equal to or greater than that specified, and no individual test is more than 500 pounds per square inch below the specified strength. Specification required 1 strength test for each 150 cubic yards of concrete based on the ASTM, and 1 for each 100 cubic meters based on the CSA. Concrete beams for flexural strength tests can cast and cured in a similar manner. Hardened concrete can be tested for strength using a rebound hammer, by testing sample cores out of the concrete, or by various other methods that can be employed. Concrete maturity. indicates the degree to which hydration has processed. This concept is used to measure early strength where it is critical. Examples of critical situations are highways that have to be repaired and reopened without delay, or when freezing is expected within hours. Maturity meters have been used to measure the heat of hydration in concrete, and of course, we're looking at the strength. The probe, coated with grease, is inserted into the concrete when poured. However, a void is left when the probe is removed and must be repaired. More modern technology uses the maturity method, and it's outlined in ASTM standard C1074. The strength maturity relationship for a mix is established in the laboratory. The temperature or maturity readings are taken through sensors embedded in the concrete every half hour for the first 48 hours and then hourly thereafterwards. The reading can be compared with the calibration results to reliability to determine the strength of the concrete at any given time. Special concrete technology is evolving rapidly within the industry. The use of many improved types of admixtures and supplementary cementing materials have become widespread, of course, in the 80s and 90s. They have made possible the development of very high strength concrete with substantially improved durability. Of course, we discussed some of this already. And other types of concrete have been used in special situations or are in the trial and evaluation stages. As emphasized, the American Interstate Highway System has changed from construction to rehabilitation, and the SHRP has provided a number of projects involving bridge overlays, patching, and full depth pavement replacements. The use of rapid strength concretes, high cement contents, and accelerating agents has allowed highways to be reopened in 4 to 6 hours. Other trials have resulted in adequate strength gains within 12 to 24 hours, and in special cases, after only 2 hours. Final evaluation of these projects is continuing. Lightweight concrete can be divided into 2 categories. We get structural lightweight concrete and, of course, insulating concrete. Lightweight aggregates, expanded shale, slag, or certain types of volcanic rock are used. Structural lightweight concretes have densities of about 90 to 150 pounds per cubic foot, and strengths are usually, but not necessarily, somewhat lower than normal concrete. Insulating concretes have low strengths with densities around 15 pounds per cubic foot. Heavyweight concrete are used for shielding purposes in the concrete or nuclear reactors at power plants. Heavy aggregates such as iron ore particles are used, and densities are as high as 200 pounds per cubic foot have been obtained. Architectural concrete, usually produced in precast plants, can be made with a wide variety of surface finishes, produced using different colors. Exposing aggregates, sandblasting, brush hammering, and other techniques have been used. Again, basically, what has the architect or the design professional spec'd out, or what look are they looking to obtain or have? Forms that produce special textures and rough surfaces are also used. Facing panels and other building components are manufactured. Fiber reinforced concretes contain various types of fibers, such as steel, glass, synthetics, and are added during the mixing operation. Synthetic fibers include various things as plastic, nylon, polyethylene, polyvinyl, and so on. Asbestos fibers formerly were used extensively. Of course, we know what these asbestos fibers do or the health risks with them. Fibers can help prevent surface cracks and improve toughness and flexural strength in the concrete. Impact resistance and fatigue strengths are also improved. Fiber reinforced concretes have been used in thin structural sections to replace reinforcing rods, road locations that carry heavy loads, bus stops, intersections, transport loading docks, and other areas for floors subjected to impact loads and, of course, similar loading situations. Unshrinkable fill is another type of concrete that we can use. Trenches are often opened in urban and rural roads to repair or provide new utility connections. The backfill operation is very difficult to control, and usually a depression forms in the road within 1 to 2 years. Of course, we see this all the time. Road openings happen. Later on, years later, we get that depression. Unshrinkable fill has been used as a solution to this problem. The material is a weak concrete mix with a maximum strength of about 60 pounds per inch. This backfill requires no compaction, is strong enough to resist all settlement stresses, and can be easily excavated in the future if necessary. The cost is reportedly competitive with properly compacted granular backfill construction materials. Rollcrete, a roller compacted concrete, has been used in dam construction to place and strengthen concrete economically. A relatively low-cost mixture with minimum water and cement content can be placed using large, economically earth-moving equipment that we all pretty much have access to. Concrete is then compacted by rollers, resulting in much higher strengths than could be obtained with a similar mix without this type of compaction. Polymer concrete or polymer impregnated concrete contains organic materials that combine and grow into polymers, filling small pore space in the concrete itself. In polymer concrete, the material is added during the mixing, whereas in the second type of concrete, surface is coated and the liquid soaks into an existing slab. These concretes have very high strength and remarkable durability. Bridge decks subjected to the application of de-icing chemicals have often deteriorated rapidly due to the corrosion of the reinforcing steel. Polymer impregnation has been used successfully to protect these surfaces by preventing the intrusion of the de-icing materials or chemicals. Alumina cement is manufactured in the same manner as Portland cement. However, the main product is calcium aluminate rather than the calcium silicate. This cement hydrates rapidly, reaching high temperatures in 1 day or less. The rapid strength gain of alumina cement makes it useful in many construction or repair situations in which time is important. It is also used in very cold climates where the large quantity of heat liberated and the rapid rate of hydration often allow construction to proceed without any other type of protection. Alumina cement is more resistant to most types of chemical attacks than ordinary Portland cement. Organic impurities in sand. Of course, the purpose is to determine if there are organic compounds in sand that may be injurious to the cement or the concrete itself. The theory is organic coatings on sand may retard setting of the concrete itself. The amount of these impurities can be checked by adding sodium hydroxide to the sample. The color of the sodium hydroxide solution changes depending on the amount of organic material in the sand. Slight color change indicates that the amount of organics is not too injurious. However, if the color becomes dark amber and sand should be rejected. A color or a standard color chart is used to measure the color change. This contains 5 organic color plates. We get 1, 2, 3, 4, and 5. Color 3 is, of course, the dividing color. Let's take a look at the dry rotted density of the coarse aggregates. The purpose is to obtain the approximate maximum dry density of the coarse aggregate for a specific concrete mixture. It's the most economical concrete mix that contains the maximum amount of coarse aggregate particles. The coarse aggregate is placed in a container of known volume and then rotted and worked to get as many pieces as possible in the container. Of course, this is going to result in the density or the measured or the maximum density that we can get. If the concrete mix can be designed using this amount of coarse aggregate, the amounts of sand, cement, water required to fill the voids or spaces between the coarse particles or aggregate particles will be at a minimum. Slump of the concrete, the purpose, again, we talked about it earlier, it's the workability of the concrete. And the theory is the sample of the concrete formed into a cone slumps or falls in a measure of its consistency and placing or flowing characteristics. Of course, we need a slump cone, a tampering rod, and a ruler. Air content with the pressure meter. The purpose, of course, is to measure the air content of the fresh concrete. The theory, the pressure type air meter has an air chamber on the lid. A hand pump allows this chamber to be pressurized. A bleed valve allows the pressure to be adjusted, and an operating valve allows air to enter the bowl containing the concrete. Let's take a look at casting concrete test cylinders. And the basic purpose is to determine the compressive strength of the concrete mix. So the theory is Portland cement concrete is usually measured as the compressive strength in a 6x12 cylinder and basically a 28-day casting. And we have some optimum conditions that we're looking to meet, which is 100% humidity and 23 degrees Celsius plus or minus 2 degrees Celsius. The apparatus used, cylinder molds and tampering rods or vibrators. Let's take a look at the compressive strength of concrete. And again, the purpose is to determine or measure the compressive strength of the Portland cement concrete. The theory, we take the concrete, we put it in the concrete cylinders and we let it age. We take the true strength of the concrete in the cylinders as measured. It must be capped with a hard material to provide a flat, level loading surface with a plane perpendicular to the axis of the cylinder. A sulfur and fine sand mixture is usually used for this purpose. We look at the liquid at 130 to 145 degrees Celsius and hardens rapidly as it cools. To fail this cylinder, it must be loaded at a constant rate of between 20 to 40 psi per second. Trial mix water cement ratio. Of course, we want to find, or the purpose is to find the optimum proportions of cement water aggregate and add mixtures for a concrete mixture. Of course, we have the apparatus. We've got a mixing pan, mixing tools, balances, slump cone, volumetric container, strength test molds, and for air and trained concrete, a mechanical mixture must be used and an air meter will be required. Trial mix ACI method. Again, we're looking for the optimum portions or proportions of cement, water, aggregates, and add mixtures for a concrete mixture. Again, our apparatus, we need a mixing pan and tools, balances, slump cone, air meter, volumetric container, strength test molds. This concludes the Module 6 lecture on Portland cement concrete. And again, please make sure you look at the PowerPoint presentations for the examples that will assist you in solving the assignments that are related to the Module 6 lecture.